Is that it? We're on.
Yeah.
Mm.
Thank you for bearing with me in that tough time.
No worries.
All right, let's get rolling. A lot of slides, not much time. Some say it can't be done. I agree. So that's the talk. Thanks for coming.
Thanks for having. Lovely, it's riveting.
That was
Really
amazing.
good. A lot of effort. So we're in the 50s. That's where we go back to. Back in the 50s, right?
Yeah.
And we come across this character, Richard Bellman.
Mm-hmm.
Bellman Ford algorithm, graphs, if you're a fan of the Bellman. And we actually have this guy here, Charles, who was running the defense. He was like head of the defense force in the 50s in the US. And basically, he hated mathematical research. He wasn't a fan of any research. He was just a big, like, no research kind of guy. So what Richard said was like, okay, cool. What if we did dynamic programming for research? He just basically had some fancy name that he thought he could like trick the defense minister into like giving them funding for research. So that's actually where the name comes from. It means nothing. It means nothing more than a name to convince someone to give you money.
Familiar with that. Is it, are we talking in the UK or in the States?
No, in the States.
Okay.
So really what dynamic programming is about is making recurrence relations fast. But what the hell are recurrence relations? It's just fancy names on fancy names. Like recurrence relation is just a mathematical name for recursion. So let's define a function that given an input x doubles it, right? Wasn't too hard to think of what a function might look like that. But here we are, right? f(x) equals x times 2. And that's all we've got to do. So how can we achieve the same result with recursion? So we want to do the exact same function, but we're going to recursively define, 2 times x. And this is actually what it looks like. So we can say f of x, right, is f of x minus 1 plus 2. That is actually equivalent where the base case is f of 0. So let's just kind of like, what does it look like with f of 3? So what is 3? What's the double of 3? So we call f of 3 and we get f of 2 plus 2, right? Then we get f of 2, right, which is 2 minus 1. Then we get f of 1, 1 minus 0, and we get f of 0. We hit our base case, so that's 0. So then we kind of walk back up the chain. So now we can substitute f of 0 for 0 and get 2. Then we can substitute f of 1 for 2 and get 2 plus 2. And then finally, we can substitute f of 2 for 4 and get 4 plus 2 is 6. So are we all convinced that like those two things are the exact same way to implement, 2 times?
Okay.
Like this.
I'm convinced.
I've hidden you, which is not going to help.
Let me just have a look in my book here. Cameron. Oh yeah, I understand.
Yeah, you got it? You got it.
Yeah.
So all we're saying here is that if I want to know what the double of any number is, right, I can basically keep subtracting, or I can keep calling the function, right, with x being 1 less. So I can say the double of 3 is the double of 2 plus 2. And the double of 2 is the double of 1 plus 2. And so eventually you create this expression, which is essentially just, for f of 3, it looks like 2 plus 2 plus 2. Because you're kind of like, every time you've called the recursive case, you're kind of given another 2. It's not that, you mean...
Oh, yeah. Yeah, okay.
I mean, it's like going like, f of 2, what's that? Okay, that's f of 1, that's f of 1 is f of 0, and then we kind of go back up.
Mm-hmm. Yeah.
So, cool. So if it's there, so f of 0, f of 1, f of 2, f of 3, right, is double of 0 is 0, double of 1 is 2, double of 2 is 4, double of 3 is 6. So we kind of have, given some 0, and given some number, we have an output. We have this kind of sequence. Sequence 0, 1, 2, 3 maps to 0, 2, 4, 6. And we get there from the start of the sequence to the end of the sequence, we get there by just adding 2. So a little fun fact is, what we just defined there is called an arithmetic sequence, which is essentially just to say it's a sequence of integers such that they're separated by some fixed amount. Right? So sometimes you'll see it written as A of n. You know, those two things are exactly the same, or you might see it written like that. They're all describing the same thing. And so you can actually generalize this. So you can say, if I have some function which is defined as itself minus 1 plus some constant m, and the base case f of 0 is b, then you essentially can get this equation, which just says that, okay, cool, the function is equivalent to mx plus b, being we're going to times x. We're gonna add x to itself m times, which is the kind of what's happening with the f of x equals f of x minus 1 plus b, and then the plus m, then f of 0 is b, so that's kind of the initial case. And what we've just described there is just a straight line. So arithmetic sequences are basically what you get if you kind of look at all the points along a line. Again, not that important, but just a fun little tangent. And in our case, we replace the b, the m for a 2, the b for a 0, and we get 2 times x plus b, just 2 times x plus 0, which is 2x, which is a 2 times x. That's kind of how we got to the same place. So when are these recurrence relations handy? Got no idea. So let's take an example. Suppose we had a farm and Leonardo de Pista gives us a single rabbit, right? He's in the area. He goes, look, interested in a rabbit? I've got one here, I've got to get rid of it. You know, do you want to take it? And the farmer says, yeah, you know what, I'll have it. He then tells the farmer that in 2 days' time, the rabbit will give birth to a single rabbit every day thereafter. So he has to wait 2 days before the rabbit will start, you know, producing a rabbit, giving birth to a rabbit every day. So day 1, rabbit won't give birth to a rabbit. The next day still won't, but day 3, it will then give birth to a rabbit. And then every day thereafter, it will give birth to a rabbit. Then, after each rabbit is born, it also has to wait 2 days before it can start giving birth. So it's kind of like, you know, each rabbit has the same condition in the sense that once they're born, they've got to wait 2 days before they can start reproducing. So the farmer thinks to himself, how many rabbits will there be after n days? And whenever you've got to think about like some problem of n, it's generally easier just to think of like some concrete case, work out what pattern you see, and then see if you can generalize from there. So how about 6 days? How many rabbits will there be after 6 days? So let's take day 1, right? We have 1 rabbit. Day 2, we also have 1 rabbit because we have to wait 2 days before we can, this initial rabbit can give birth to the next rabbit. So day 3, rabbit A gives birth to rabbit AB. So here we can think of A, B being A is the parent, B is the child. So day 3, we have 3 rabbits, right? Because rabbit A comes along. Rabbit A then gives birth to rabbit AC because it has to give birth to a rabbit every day. But our rabbit AB can't do anything yet because it hasn't waited 2 days.
But who's having sex with rabbit A?
Hey, it's a little bit of a Jesus and the Mary kind of story here.
Dave.
So now we get to day 5, right? A bit more complicated, but the same principle. A comes along to the right. It gives birth to AD. AC comes along, can't do anything. AB comes along, but this time AB's waited 2 days. So it can give birth to ABA. So we have 5. And basically this pattern goes on. If you go to the next step, we see that you actually get 8 rabbits. So on the 6th day, you have 8 rabbits. So how can we generalize what's happening here? And if we kind of like, you know, concentrate on the n equals 5 case, what we can see is that if we look at the day before, we know each rabbit has to come to the next day, right? So we can just move them into the next day. And then we have to think about like, all right, which of these rabbits will give birth to another rabbit? And we know that the rabbits which were there 2 days ago must give birth to a rabbit today. So each of these rabbits, right, are also going to give an offspring. And so we can think about this as at day 5, what you're really saying is it's the day before plus the day before that. In this case, it's day 5 is going to be day 4 plus day 3. And this thing says the exact same thing. Some arbitrary day n is going to be the day before plus the day before that. And that is the Fibonacci sequence, this guy. The Leonardo, Fibonacci goes, ha ha ha, you got it, I got you real good, right? So we exit the mass world and we come to the JS world, right? Okay, we love the mass, it's great to think about, but what does this mean concretely? What are we actually doing? Let's get our our hands dirty with this stuff. So because of time, I've just gone ahead and just implemented this instead of muck around with that. I'm just going to try and share a different screen. But we have to start somewhere, right? So this is like the most naive case. We basically just translate exactly what we had in mass into a function called fib, which the base case just says, okay, if n is 1 or 2, we return 1, right? So this is day 1, day 2, which we had 1 rabbit. Otherwise, the amount of rabbits is going to be, the day before plus the day before that. So this is great, right? It works. Fib of 1 is 1, fib of 2 is 2, fib of 3 is 2, fib of 4 is 3, fib of 5 is 5. But it is so slow. Like if you look at fib of 50, that took 2 minutes to compute. So what do we do about it? What do we do about this slowness? How do we, that's just not good enough. There must be a better way. So let's take a look at our example of f of 5. Now, f of 5, so here f just means this is the Fibonacci sequence. F could be number of rabbits at day n, right? It's whatever you want it to be. But basically, I've just shortened here, so less typing. So to compute f of 5, we know we have to compute the day before and the day before that, right? There's like 2 calls, two recursive calls we have to make. So we have to call, in this case, I've said f of n is f of n minus 2 plus f of n minus 1. So let's start with the minus 2 case. So we've got to compute f of 3 first. Then f of 3 is like, yeah, but I need to compute f of 1 before I can do anything. And f of 1 is a base case, so it says, okay, cool. F of 3 goes, cool, I've computed f of 1, but now I need to compute f of 2 before I can say anything, right? F of 2 says, well, I need to compute f of 0 and f of 1 before I can return anything. And eventually that gets returned up to f of 5, and f of 5 goes, oh great, I've computed f of 3, but I still need to compute f of 4. So then it just does the same thing, right? So I need to compute f of 2 and blah, blah, and on and on and on. And what you can see is that we're repeating a lot of computation. We're calling f of 1, f of 0, what's that, like 8 times or whatever, right? If you look at f of 2, we're calling that 3 times. We're recomputing that 3 times. And f of 3, we're recomputing that twice. So we're doing a lot of extra work that we don't need to do. And so the light bulb moment is, what could we do? Or rather, what if we could store these interim results? What if we could store f of 2 or f of 3 when we compute it once, and then when the other functions need a value, they can just look it up in a table or something, say, yeah, I've already computed that, I don't have to do it again. And that's effectively what we're going to do here, right? We're going to replace the first time we compute f of 1, we're now going to replace it with some cache value. When we compute f of 2, we're going to replace it with some cache value f of 2. And so what we can do is we can replace these repeated computations with like a cached version of that value. So now our tree goes from looking like this to looking like this. So, dynamic programming at the heart of it is all about caching. It's all about how do you take a recurrence relation, some recurrence, and cache it in a way that you can reuse those already computed results. You only want to compute some subproblem once and that's it. You want to reuse it from then on in. And this is where the technique of memorization comes into play. Right? Memorization really is just about, it's like the implementation of how you do the caching, get this caching idea to work for recurrences. And you'll see sometimes the memo function. And essentially, so that's what we're going to do, right? We're going to have this memo function that says, cool, you know what I'm going to do? Like, you're going to give me a function, right? I'm going to memorize it, but I'm just going to take the function and I'm going to look at the argument that you try and pass into it. And if I've already seen this argument, I'm going to cache it. I'm going to return you the cache result. Otherwise, I'm like, well, I'm just going to set this to the cache. I'm going to set this argument to be the cached version, and I'm going to return that. So, you know, it'll only ever be computed once. So now we define the Fibonacci sequence as this like memorize function, right? We say we're going to pass in Fibonacci, right? But look at the recurrence case on line 5, or line number, oh, there's kind of 2, look at the bottom line number 5. It calls fib_m, so it's actually calling this memorize Fibonacci function, not the original Fibonacci function. So this is just how you can abstract the memo into its own function, where you don't have to really think about how to memorization. You can just worry about writing the recurrence and let memo function do the caching. So now if we look at the times, fib of 50 on our fib_m implementation is 0.073 seconds. So we've gone from over 2 minutes to less than a second by just doing this, by just adding an idea of caching previous results. So that's meant a huge difference in performance, you know, in time to compute it. I mean, it really comes back to if you look at how the recurrence one works. Essentially, like to compute some Fibonacci of n, you've got to do 2 to the n calls, whereas with the dynamic version, you only if you're calculating the Fibonacci of n, you will only ever have, you know, from say Fibonacci of 10, you might call 10, then 9, then 8, then 7, then 6, all the way to 0, but you only ever do it once. You'll never have to recompute f of 2 twice, or f of 3 twice, or 10 times, right? So this n just means that you'll always do no more work than the number n that you pass in. And that's the magic here of DP, right? That very often it takes problems which are exponential and it makes them linear, right? It takes problems where it should take years to compute and it can compute it in a few minutes. And that's really the difference here in performance. Like that's like the mind-bending thing, that such a simple technique can give you a huge leap in runtime. But there's a problem. And if we try to do 6,000, we get a call stack exceeded. Because what's happened is it's gone, cool, we're not recomputing, you know, we're not recomputing things we've already seen, but we're still recursing. And so when we come against the stack goes, hey, I've only got so much memory here. I can't let you just keep recursing, creating stack frames and putting on top and top and top of each other before I run out of memory. And I say, hey, that's it, game over. So what if you wanted to compute Fibonacci for 10, you know, in his case, only 6,000. You want the Fibonacci for day 6,000, you know, that's like 20 years into the future. So what if you wanted to know what it is in 1,000 years in the future? Right? So we need to get around this somehow. And so could we do this iteratively? If you can do it iteratively, it means that we don't create stack frames, and basically we can use one stack frame to keep computing the result. So if we look back at our f of 5 again, our Fibonacci of 5, this is what we kind of left with, this idea that we're now just going to cache the subtrees that we see. But there's something interesting happening. If you look at the order in which the functions are called, there's a certain pattern that comes about. So the first thing that's called is f of 1, right? Because f of 5 says, well, I need to call f of 3, and f of 3 says, well, I need to call f of 1, but f1's a base case, so we stop there. So then once we go for 1, right, the next thing that's actually returned or resolved is f of 0, right? Because we go f of 2 says, well, I can't do anything until f of 0 is finished. F of 0 is the base case, so it returns. And so if we just kind of like walk through the order in which functions, finish the computation, we get this ordering. And so that's the order in which, f of 5 is computed, by first calling f of 1, then f of 0, then looking at cache of 1, looking at f of 2. But the beauty of this is that we can actually remove the cache nodes because we know they can't cause recursion because we're just looking them up as a value in a map. We're saying, give me what's the value for 1. We know it's already been computed, so we can remove them. Now, we're safe to rearrange the base case nodes, right? F of 1, F of 0, right? Then there's no dependencies on those. So it doesn't matter if you go F of 1 first, F of 0. That's not true for F of 5 because F of 5 needs F of 3 and F of 4 before it can return its result. So let's swap them. And then we get, oh, look at this. To compute F of 5, you've got to compute F of 0, then F of 1, then F of 2, up to 5. And that's really the key here, right? What we just did then was another fancy word, which is a topological sort on the tree, which just says, give me an ordering, give me just some sequence of nodes in that tree, and that's the sort, right? You just sort them into a certain order. But the power here is that now we don't have to actually do any recursion. We can just start at 0 and work our way up to 5, just with the for loop. So all we do here is we say, okay, the base case is 0 and 1. So we just set the cache to be the value for 0 and 1 is f of 0 is 0, but f of 1 is 1. And then we start at 2. And all we do is we do, like this should look kind of similar, right? If you replace cache with f, you kind of see that f of I is f of I minus 1 plus f of I minus 2. But here we're just using the cache, right? We're looking into the cache and saying, well, I know that f of 5 is f of, say cache of 5 is cache of 4 plus cache of 3. Well, you know that that's already been computed earlier in the for loop. So, you kind of just moving through it one at a time and you're kind of combining the results you've used along the way. So here there's no recursion. We've kind of reduced this down to just an iterative version of the exact same thing, but we're now explicitly walking, like starting from the smallest case, getting to the more complicated cases. And so now you call it 6,000, even though it says infinity, that's just because the numbers in JavaScript don't have enough. They don't use the begin implementation, so they have like a maximum value that they can take. Otherwise, after that, it's just infinity. But theoretically, we could compute this for infinity, right? Because we're just going to keep moving the for loop. Nothing's going to stop us. We're not going to run out of memory as long as the integer can just keep growing as it needs to be. We're back. So you think, okay, cool. We're very much. That's great. Now we can given any, if you want to compute the Fibonacci of any number, hey, we've got all the time in the world. We can just run that loop until we get to the number that we're trying to find out. But there is one way you can make this a little bit nicer. And the question is, do we really need to store those interim results? When I'm looking at cache of 5, right, I only care about cache of 4 and cache of 3. I don't care about cache of 2. At this point, who cares about cache of 2? I don't need those values to compute the next Fibonacci number. So to compute fib of I, which is basically cache of I, we only need 2 previous values, namely cache of I minus 1 and cache of I minus 2. And so what we do here is we just go, cool, we only need 2 variables, A and B, which will represent I minus 1 and I minus 2. And each time around the loop, we can say, okay, we're going to store A as a temp var, and then A, right, is going to be almost like our cache of I, is going to be what it was previously plus the one before that. And then we'll set B to be what A was. So you're kind of like sliding, where like each time A and B, B takes on what A used to be, and A then becomes like the next one, which is what it is once B's added to it. Now, I don't expect that this is going to click straight away, but like if you kind of like step through it, like take an example of 5, you'll see that all you're really doing here is like reassigning A and B to the 2 previous values in the sequence. But the beautiful part of this is that it's all one space, which just means that it's constant space. It doesn't mean if you give me n being a billion or a trillion or or 15, the amount of memory I need to compute it will be constant or won't have to change. Whereas before, when we stored it like a map of all the results from 0 to n, well, that means we would have, if you gave me a billion, I'd have to store a billion, integers to represent all the previous results. So this is great. This is like reduces our amount of space we need. And essentially this is about as good as you can get it. Now you've got constant space, and the computation, the time to compute it is going to be proportional to the size of the n that you give me.
So in this case here, we've got 10 minutes left. Oh, good. Perfect time for me to go questions. Well, actually, do you want to finish off before I go into questions? Or?
Yeah, I've probably got like a minute left.
But just for this one here, can I just ask quickly?
Yeah.
So if it's like 5, at that case, if so at 5, A is 4, B is 3. At 6, A is 4, B is 5, etc. That's what that's doing.
All around, yeah, exactly. That's exactly the way to think about it. That A and B will be
A is minus 1 and B is minus 2.
Yeah, exactly. That's exactly what's happening here.
Cool.
So you think, if you got this, if you got a problem that was, exponential in time and space, and then you come and say, I can make this now constant in space and linear in time, right? You'd be pretty happy. I mean, you'd be like, you're knocking off that day going, job done. Until this guy comes along, right? And he says, what about a constant runtime? It doesn't matter if you give me a billion as the number, 1,000 as the number, 10 as the number, right? The time essentially will be the same. It won't, the bigger n shouldn't mean a longer time for it to compute. This is the holy grail of computation. You can get constant, time and constant space. And so he comes up with this thing. It's a little like maths where you can solve the recurrence relation. Now he can do this because n here is an integer. It's not just some arbitrary thing. Like you use recurrence relations all the time for like graphs. You might say the shortest path from some start node to some end node is the shortest path from the all the nodes that I'm connected to. And so you can kind of define recurrences in other domains that is integers, right? But because we're talking about integers here, you can do this little trick where you can actually solve the recurrence relation using this idea of a homogeneous solution and a particular solution. But he just goes, bang. Actually, fib of n is this equation. Easy. He just goes, why are you doing this, A and B business and like copying over? Just whack it into this equation and you'll get the thing out. So that's what I did. I just converted that equation to a function called fibc, which essentially does exactly what that equation says, right? And bang, it worked, right? Fib of 5, 6, 7, 8, they all give the right result. And so really, it's in this case, we tried to solve this problem of rabbits, how many rabbits we have at day n, and if someone asks you that, if the farmer asks someone asks the farmer how many rabbits you have at day n, they could tell you in constant time and constant space what the answer is. That's it. That's
cool.
Thank you.
All right, here's my question.
Yeah.
So the fib thing is like the foobar of like this kind of stuff, right?
Yeah, definitely.
So what's the what's a real world thing where React has like a use memo method.
I mean, that memo, the idea of memo is more general than just Fibonacci, dynamic programming, right? Dynamic programming uses memorization, but in a functional language like Haskell, you can actually only have to call the function once, and then you can replace any calls to that function with the value that it returned, because you know that if some pure function takes 1 and returns 2, then it can't. Every time you give it 1, it has to give you 2. So you only have to compute it once. So you can just even in JavaScript, if you've got some function called that does some expensive calculation, you can wrap it in a memo function, which will say, cool, I'm going to record the results that this function outputs. And so if someone tries to call f of 10 or like do expensive calc 10 twice, on the second time, I'll just return back the result I computed, the time before.
Are you aware of any compilers that do all this behind the scenes without having to change?
So no, because the problem is that certainly for the case of if we take like this clever thing of doing finding a constant equation, the problem with that is that it really depends on what n is, what type is n. If n's an integer, then there's certain things you can make. But if n's whatever some data type that you defined, like a graph node, then it really knows nothing about the domain of the types that you've given it. Where what FP is usually you can take some problem, you'll start with the simple recursive solution, and then you basically try and like work it until you can get it to be, once it's working for the recursive case, then you can do the transformations to work out how to work. But yeah, I haven't come across I'm sure there's tools that will probably could like mechanically do the work of converting it, but I haven't seen it as like a compiler thing per se.
Yeah, it just kind of interested me, like similar in the way you write unit tests, if there was some compiler that could automatically see patterns and then, it's an interesting idea anyway.
Yeah, I mean,
is that what tail recursion is? Like, do you know much about that?
Yeah, I mean, tail recursion is more of it. Yeah, look, tail recursion wouldn't solve the problem of wouldn't solve the problem of like when you've got something like if I can just find the f.
Yeah. Yeah, like your first step that you showed us, going from recursive to iterative, right?
Yeah, I mean, even like if you take here we go. Oh no, I go past it. When you've got anything of the form, yeah, anything. See how to compute f of n, you need to compute f of n minus 1 plus f of n minus 2. Now, if to compute f of n minus 1, it's to compute f of n, if you said that's equal to 5 plus f of n minus 2, and you could do tail call recursion, because you could say, the last thing we do is recursion, which means we don't need to like create another stack. We can just use our current stack to then like basically let f of n minus 2 be the, take our current stack. So tail call recursion only helps you when it's like the last thing you do and you return it. You return that recursive call. It won't. This is the problem. Like this kind of operates one level, I guess above what once you've like implemented whatever thing you're trying to do in a language. At that point, it doesn't know about the semantics of what you're doing. It will just try and run whatever it is. And those tail call recursion will try and help, but this is like fundamentally you have to change how the problem is stated so that you can get it to look like something you can do in an iteratively fashion.
Cool.
Okay. Cool.
Where to from here, Cam?
I would say give the problem of the bar of gold, breaking up the bar of gold, give that a crack, right? Because you use the same thinking that we did here to solve that problem, right? So if you've got a bar of gold, you can think of it like, well, you don't know, the problem is, right, that if you take a bar of gold that's length 10, if you split it, say at like the first, say you can break up into 10 bits. If you break it up in the first bits, you got 1 and 9. If you break it there and then see what could you get for the 9, it might have been better if you broke it up at the second slot and then did 8, right? But you don't know when you break it up at 1. So you kind of have to explore the whole space But you need to think about recursively, like, oh, well, you know, if I know what the cheapest, if I take a bar and I know that if I split it up into 2 bits, I know what's the most I can get for that. Or if I take a bar of 3, I know what the cheapest, or what the most I can get for a bar of 3. Then I know what the most I can get for a bar of 4. And I know what the most I get for a bar of 5. And so like a bar of 6 will be dependent on how much you can get for a bar of 5, 4,